On screen we have an infinite sum or series, it's the same thing, and we're looking to see if this converges to a limit. And to do this we're going to use the formal definition introduced in the last video, so if you didn't see that be sure to check that out, and that's to do with the partial sums. So if the partial sums of this series converge to a limit as n goes to infinity, then the series converges. So the first trick we use here is if you use partial fraction decomposition, you can see that 1 over k times k plus 1 is equal to 1 over k minus 1 over k plus 1. And this is quite helpful because now when we define the partial sums, so bear in mind the partial sums Sn is equal to the sum, in this case from k equals 1, because that's our p, from k equals 1 to n of 1 over k times k plus 1, but that's this sum here, so we'll write this, and you'll see why in a second. And this is clearly equal to, so we get 1 over 1, so 1 minus 1 half. Okay, so that's the first term, and then we can take k equals 2, so we get plus 1 over 2 minus 1/3, then we take k equals 3, and so on, you get the point, until we get to our final one here, 1 over n minus 1 over n plus 1. But it's clear here that every time we're subtracting a half here, the next term has the same value but opposite sign. So this minus a half cancels out with this 1/2, and this minus 1/3 would cancel out with a third here, and this 1 over n cancels out with a minus 1 over n before there, because the term before would be when k is equal to n minus 1. So the minus k minus 1 over k plus 1 is equal to minus 1 over n. So you can see that all the terms cancel out in the middle here. So the partial sums n for all n is equal to 1 minus 1 over n plus 1, and Sn clearly tends to 1 as n tends to infinity, because this 1 over n plus 1 tends to 0. Okay, and therefore our infinite sum from k equals 1 to infinity of 1 over k times k plus 1 converges to 1. Okay, so hopefully this example helps you get your head around the idea of the partial sums. Okay, so in the last part of this video we're just going to introduce a theorem, and this is called the divergence test. So if the terms in a sequence ak do not converge to 0, then we can say that the sum from k equals 1 to infinity of ak diverges, meaning it does not converge to a limit. But note, it's important to recognize that this does not mean that if an infinite sum of AKs which do converge to 0, that doesn't mean that definitely converges as an infinite sum. Okay, so that's important to know. All we can do with this result is if AK does not converge to 0, we can instantly say the sequence diverges. If the AKs do converge to 0, we have to do some further investigation. So when could we use this test? I mean, say we have the sum from k equals 1 to infinity of 2k. I mean, it's pretty obvious this is going to diverge, but this test tells us that because ak is equal to 2k does not tend to 0 as k tends to infinity. There's obviously some more profound examples, I guess, where it's a little bit less obvious what's going on, But this is a nice test to just quickly rule out the possibility of convergence. As I say, if this sequence doesn't go to 0. Okay, so hopefully you understood this video. In the next video we'll probably follow a similar format. We might use this divergence test in a couple more examples. So say a few more slightly maybe a counter example to show that when AK tends to 0, that doesn't mean we necessarily get convergence here. And then we'll introduce a new limit test as well, and that's very much how this series is going to go. We'll just be introducing tests so we can see whether series converge or diverge. We might chuck a couple of proofs in there as well, just to mix it up. If you did enjoy this video, please be sure to like and subscribe. If you've got any questions about this or anything else maths related, let me know down in the comments. But for now, that's it, and I hope to see you in the next one.